In this part of chapter 7, we will be discussing cycloalkenes, their stability, and we will be looking at reactions where we can make alkenes out of an alkyl halide versus alcohols. In this part, we will be discussing E1 versus E2 of those reactions. So starting with the cycloalkenes, similar to the cycloalkanes, the smaller the ring, the more eclipsed hydrogens there will be in the structure. And that justifies the stability of a larger ring compared to smaller rings. So if I take cyclobutene versus cyclopentene, we could see here through the hydrogenation reaction where the heat of hydrogenation, it's actually higher for the cyclobutene compared to the cyclopentene. So that tells me right there that the smaller the ring, that the more strain it's going to have, and therefore it's going to affect its stability. And compared to the straight chain alkene, I could see clearly that the shape around the alkene is trigonal planar. So the bond angle should be around 120 degrees. But when it's a cycloalkene, clearly the bond angle will be much more strained. So that angle becomes 60 degrees. So that tells you right there, in terms of stability, it's dramatically affected when you go from a cycloalkane to a cycloalkene. Keep in mind that the IHD is minimum of 2 because you have the alkene unit and you have the ring. When it comes to larger rings, now these structures that do have a ring and have a double bond in it, they tend to always be in the cis form, unless there are 8 carbons within the ring, like a cyclooctane. When it has a double bond where it becomes a cyclooctene, then it may have the possibility of forming a cis versus trans. So the cis will still be more stable than the trans due to strain within the structure. But when you have a 10-member ring or more, and it does have an alkene unit within it, the cis and trans, they become very similar in terms of stability. So that's important to keep in mind, that if you have a 3-member ring, 4-member ring, 5-member ring, all the way to 9-member ring, there will the cis will always be more contributor or exist in that in much more proportion. Now the 10-member ring or higher, there you will be the cis and trans will be very similar in terms of stability. And keep in mind that you cannot have cyclopropene or cyclobutene or cyclopentene or cyclohexene or cycloheptene in other form other than the cis form. It cannot form a trans form in those structures. Britt's rule, what is this rule about? If you have a bicyclic compound, bicyclic alkene, and the structure will prevent having a double bond around the bridge. So those fused rings, obviously the bridge will not have any carbons within it. But if you have a bridge in the structure, the double bond preferably to be away from the bridge. That's what this rule is about. So if I look at this example, what it's telling me which of those is stable and which of those is not stable and why. This structure right here, you could see the double bond is basically on a bicyclic compound that is not bridged, it's fused. So therefore, it will not affect the strain of the structure. Therefore, it will be a stable compound. And this structure, though, the fact that the double bond is around the bridge and it has 6-member ring, then the structure will be unstable. So in order for the double bond to be on the bridge and to make the structure still stable, it prefers to have at least 8-member ring in that bicyclic compound. Like in this example, you could see here that the bridge is near the bridge, the double bond is near the bridge, and the structure, it has 8-member ring. Therefore, it is okay, and it is a stable compound. The 4th one has a double bond away from the bridge, so it wouldn't affect any stability factor in the structure. Therefore, it will be a stable compound. In terms of physical properties, usually alkenes, similar to alkanes, the more branch the alkene does have, the lower the boiling point will be. They are less dense than water, and the double bond create some polarizability due to the pi bond. So therefore, it may have some dipole-dipole interaction that will contribute to the boiling point. So you will always find that alkenes have a little higher boiling point than alkanes, comparable carbons, of course. And keep in mind that the dipole moment will depend on the substituents on those alkene units. Synthesis. We will learn in this chapter how to synthesize alkenes. There are two approaches how we do that. We could start with an alkyl halide to make an alkene, or we could start with an alcohol to make an alkene. Now, the alkyl halide approach may have actually two pathways. It could be an E1 or an E2. What we learned in a previous chapter, nucleophilic substitution chapter, we learned in there that there is an SN1 and SN2 types. And the difference between them, as we've seen in chapter 6, that it basically several factors, one of which is the mechanism. Second is the alkyl halide type, which one would be more reactive in either type. And we also seen the effect of the leaving group and the stereochemistry as well. Similar to that, we're going to be discussing actually in this part. E1 and E2, they have very similarity when it comes to their features compared to the SN1 and SN2. So the dehalogenation of vicinal dibromide is also another way how we could make alkenes. This will be discussed actually in a later chapter. So in this chapter, we'll be discussing the other three routes. So starting with alkyl halide approach. So we've seen here that the E1 and E2, similar to what we've seen in the SN1 and SN2, that the E1 will go through the very first step, that is the rate determining step, that is the leaving group will be kicked off to form a carbocation. So once the leaving group is out, you see a carbocation getting formed on that carbon, and that will be the rate determining step. This is the intermediate in any E1 reaction. And while in the E2, there will be no carbocation formation. It will be a concerted mechanism in which you have the strong base basically abstracts a hydrogen, and that hydrogen has to be on the alpha carbon adjacent to CX. And we will get to a point where, what if I have more than one hydrogen on an adjacent carbon? There will be a rule to follow. But in this case, the hydrogen, whether you pick it from this carbon that's an ethyl or this carbon or that, it's the same. So picking a hydrogen from the alpha carbon adjacent to the CX will automatically be basically moves that single bond to make a pi bond eventually, and the leaving group will be kicked off at the same time. This will be the way how E2 will go through a reaction. So this is the concerted mechanism that we have seen similar to it when it comes to an SN2. Now, the carbocation formation in the E1, that opens up the possibility for having rearrangement. This phenomena, we've seen it in all the reactions that do have a carbocation. The moment you form a carbocation, there is a possibility for 1,2 hydride shift. And if there is no hydride to shift, then there will be a 1,2 methanide shift. Not every single time you form a carbocation, there will be a rearrangement. Obviously, the rearrangement will only be done if there is a possibility to form a more stable carbocation. Why? Because the more stable carbocation will push the reaction to go faster. So let's look at details. So the E1, just like the SN1, it's a unimolecular mechanism where the reaction rate determined by the alkyl halide type. So two groups will be lost, obviously the hydrogen and the halide. The hydrogen from the alpha carbon to the CX, and the halide will be basically removed once you go through the E1 mechanism, the very first step. The nucleophile has to act as a base. E1 and SN1, the fact that they're very similar, you may have some reactions that produce both at the same time. And we will see those examples. And this is the detailed mechanism. So you see the ionization happening first, and this is the rate determining step. The carbocation, obviously, the E1 mechanism will only happen if you have a tertiary alkyl halide. You will not see a secondary alkyl halide or a primary alkyl halide going through an E1 mechanism. Similar, now, when we discuss SN1, we've seen there that secondary alkyl halide may have the chance to go through an SN1 if there is a weak nucleophile or a moderate nucleophile using polar product solvent. But in this approach, the elimination approach, you will not see a secondary or primary alkyl halide going through an E1, only the tertiary alkyl halide. And it has to have actually a weak base, just such as alcohols, and it has to have also heat. So alcohols or water and heat and the tertiary alkyl halide are the three conditions to have an E1 approach. Otherwise, you will not have that. You will be doing an E2 instead. So the solvent, once that alkyl halide, once that carbocation is formed, it's going to go through the second step. That's a fast step, the elimination. So the alcohol or the water basically going to abstract the hydrogen, and that bond will basically be the source of the double bond, and that will be the alkene structure, the outcome of an E1 mechanism. In the orbital sketch, we will see that the hydrogen attached to the carbon, that orbital has to overlap with the vacant p orbital of the carbocation in order for the pi bond to be formed. So that basically becomes very important when we talk about E2, where the leaving group actually has to be in the opposite side of the hydrogen, and we'll see why that is. But in general, the E1 mechanism is going to always go through a carbocation formation. Rearrangement is always possible, and keep in mind that only tertiary alkyl halide can go through E1, and it has to have a weak base, such as water or alcohol, in presence of heat in order for this reaction to go through E1. Here you see the energy diagram. So the carbocation will be the intermediate. You have two transition states. The very first step is the slower step, and you could see here that the activation energy is higher than the second. So the reaction rate will always depend on the alkyl halide. That's why we call it a unimolecular mechanism. So Zaitsev's rule. This rule becomes very important when we have more than one hydrogen to be abstracted. What is that supposed to mean? If I have a structure like this, I have a carbocation sitting on a carbon that has a methyl versus ethyl. So this carbon is a primary, this carbon is a secondary. So once that carbocation is formed, then the base is going to abstract the hydrogen. Which one is going to abstract? Is it going to abstract the green, or is it going to abstract the blue? Well, the green is going to give me 1,2 disubstituted alkene. The blue, once it's being picked up, is going to give me a double bond in here where I'm going to have a trisubstituted. So Zaitsev's rule comes in and states the following. When you do E1 reactions, every single time you're going to be forming the more substituted alkene according to Zaitsev's rule. So that applies only if I have more than one hydrogen to be possible to be abstracted. But if I have, like the example that we've seen previously, that there is no difference between picking up this hydrogen or that hydrogen or that hydrogen, then obviously you're not going to have to worry about Zaitsev's rule in this case. So that's important to keep in mind, that Zaitsev's rule has to be applied every single time you go through E1. In fact, it also appears in the E2, but it will be evaluated, or it will be actually looked up a little different considering the base being used. So the alkene stability, as we've seen here, the fact it's tetrasubstituted, the outcome of this reaction, that justifies why this product will be the major. We learned previously that in terms of substituted alkenes, the tetrasubstituted alkene will be the most stable. And in that study, we use the heat of hydrogenation as a factor. The more exothermic the reaction, which is the hydrogenation, the more indicative that I have an unstable alkene. So the tetrasubstituted will release the least amount of energy. Next would be the trisubstituted. Next would be the trans disubstituted. Next would be the geminal disubstituted, and then the cis disubstituted. And the monosubstituted will be less stable than the disubstituted, and you have the least stable form of alkenes that will be the ethylene, CH2 C double bond, or CH2 double bond CH2. So the disubstituted will be less stable than the tetra, therefore it will be the minor, while the tetra would be the major outcome. Now, opposite to E1 will be the E2. And that's where a lot of chemical reactions will go through in terms of mechanism, if it's an elimination reaction. E2 reaction, it's a bimolecular, so it's going to depend on both the base and the alkyl halide concentration. And this reaction will always require a strong base. Examples of strong bases, these are the ones that are going to come from an acid that has a pKa of 15 or more. So for example, water gives me OH minus. That's a strong base. Alcohol has a conjugate base, that's the RO minus. That's a strong base. All of those alkoxides are strong bases. NH2 minus, that's amide coming from NH3. NH3 has a pKa of around 33. So it's going to give me a very strong base. So all of these bases are strong bases, and they are common to be used actually in elimination reactions. And remember, it's a concerted mechanism. So the base will pick up the hydrogen. At the same time, the leaving group is kicked off. And in between, you will have basically the pi bond getting formed. And in order for the pi bond to be formed, it's going to actually go through, as we've seen in terms of orbitals, we're going to see that in a second. So the alkoxide, when it faces a tertiary, this is a tertiary alkyl halide, and the fact that it's using a strong base, not alcohol. So if this reaction would have been done using alcohol, and the fact it's a tertiary alkyl halide, there is less chance that it's going to go through an E2. It will go through E1. But because of the fact that I'm using a strong base now with a tertiary alkyl halide, this will not actually do substitution, would rather do elimination. It's too statically hindered to attack that tertiary alkyl halide carbon. So what it will do instead, it will pick up a hydrogen from the alpha carbon adjacent to CX. That will form a double bond, kick off the leaving group at the same time. So you will get an alkene through an E2 mechanism. So it's a concerted mechanism. It's a transition state exists rather than an intermediate. And the transition state will basically have the base, partially formed bond with the hydrogen, partially broken bond with the carbon, partially formed bond, that's the pi bond, and partially broken bond, that's the halide. So all that will be in the transition state. And that will give me basically the alkene at the end. The order of reactivity in an E2 mechanism, when I start with an alkyl halide, will always prefer the tertiary halide to go through the secondary than the primary. So the fact that the halide will be kicked off easier or very, very likely when it's a tertiary alkyl halide, that's why the E2 reaction will have the tertiary going faster than a secondary than a primary. It's different from an SN2. The SN2, we see in there that the nucleophile has to attack the CX. That carbon has to be less crowded, if any. And in fact, the methyl X will be the fastest than a primary than a secondary. So that's different when we're discussing elimination. Elimination, we're talking about the hydrogen being abstracted from the adjacent carbon. So that carbon, if it's sitting next to a tertiary alkyl halide, will pick up the base will pick up its hydrogen faster than a secondary alkyl halide, faster than a primary alkyl halide. What if the base is a bulky base, and that bulky base happened to be one of those: terbutoxide, diisopropylamine, triethylamine, or the 2,6-dimethylpyridine? What will happen? Well, there we will have to pay attention to another rule than the Zaitsev's rule. That is the Hoffman's rule. What's the Hoffman's rule? Hoffman's rule indicates that when you have a bulky base and you have the possibility of more than one hydrogen to be abstracted adjacent to that CX, then the base will be the determining factor. The smaller the base will pick up the more substituted, the one that's going to lead to the more substituted alkene, and the bulkier the base will pick up the hydrogen that's going to lead to the less substituted alkene. So let's look at an example. So here's one where we can see strong bases being used along with a tertiary halide being the substrate. Now, due to the fact that this is a strong base being used, I cannot think of E1. It has to be E2. Now, looking at this structure, it has two possible hydrogens to be abstracted. So the hydrogen that's in blue and versus the hydrogen that's in green. Now, which of the two the base is going to pick up? Well, if it's not one of those four bases, so you have an ethoxide as the base being used here, it will pick up the hydrogen that's going to lead to the more substituted alkene. So the smaller the base, the more Zaitsev product you're going to be making. The bulkier the base, and terbutoxide is one of the four bases that you've seen here. The bulkier the base, it will pick up the hydrogen that's going to lead to the less substituted alkene, and that's the Hofmann's product. So that's the difference between Zaitsev's rule and Hofmann's rule. It all determined by the base being used in the reaction. And keep in mind that every single time you have more than one hydrogen to be picked up by the base, that's where you're going to have to pay attention to those two rules, Zaitsev's versus Hofmann's. Zaitsev will be applied if you have small bases, anything that's smaller than a terbutoxide, so propyloxide, ethoxide, methoxide, these structures will basically be considered small bases. Then you will be picking up the Zaitsev product, the more substituted alkene. What if I have bulky base? Then you're going to have to apply the Hofmann's rule. Hofmann's rule indicates that you have to basically pick the hydrogen that's going to lead to the less substituted alkene, and that will be the major product in those reactions. Now, keep in mind, both are E2 reactions. So that should be a hint now to think of those two rules only when you have elimination that's a type 2 reaction. Stereochemistry. Also another important factor that you have to keep in mind, the fact it's a concerted mechanism. The hydrogen need to be picked up at the same time the leaving group is kicked off. That means the stereochemistry of those two, they have to basically be in an anti-coplanar orientation. What is that supposed to mean? What it means, when you have the base picking up the hydrogen, in order for the overlap of the vacant p orbital, or to be the p orbital that's going to form a pi bond above and below the bond axis, it's best to have that orbital in a way that's oriented in the opposite side of the leaving group. If I would have the hydrogen on the same side of the halide, not the anti, there will be basically a repulsion between the two, the base and the halide. So that will actually cause higher energy required to push this step to go forward. And that's why every single time there is E2 reaction, you're going to always have to pick the hydrogen that's in the anti-coplanar orientation. And it's important to keep this in mind. So if I have the halide, for example, in the dash bond, then the hydrogen has to be basically on the wedge bond, or the opposite. If I have the halide sitting on the wedge bond, that means I have to have the hydrogen that's away from the plane to be picked up by the base in order for the elimination to happen with the least amount of energy needed. So we can see clearly here that it's always best to pick the hydrogen that's on the anti-coplanar orientation to the leaving group. And again, this has to be paid attention to only when it's an E2 mechanism. In the E1, we have a carbon-cation formation, so there is no hydrogen to be abstracted at the same time the leaving group is kicked off. But in the E2, that's where you have to have the anti-coplanar orientation exist in the molecule. And what that means, hydrogen and the leaving group in the opposite sides of each other going through that mechanism. In the cyclic alkene structures, we see clearly that the cyclohalide has to be in a certain orientation. So if I take, for example, cyclohexyl bromide or bromocyclohexane treated with NaOH. Now keep in mind, hydroxide, it is a strong nucleophile, but every single time I react a hydroxide with a secondary halide or a tertiary halide, I will always get the alkene structure. And that's the reason why I rank bromide actually a better nucleophile than OH-, because OH- has a limitation. It can only do substitution if it's a primary alkyl halide. But if it's a secondary or tertiary, it will not give you a substitution product. It will give you elimination product. And this elimination will happen through an E2 pathway. So keep this in mind. So here's a secondary alkyl halide in presence of a hydroxide. What's going to happen? You're going to get an alkene at the end. But which hydrogen is going to be picked up? Well, let's draw the chair conformation, the alternative forms of the cyclohexyl bromide. You end up having one where the bromide is equatorial, and the ring flip will give you the bromide on the axial position. So between these two, we already know that this is the more stable chair conformation. However, every single time there is an cycloalkyl halide going through elimination that's an E2 type, the chair conformation where the halide is on the axial position is the one that's going to go through elimination. Why that is? Because it's going to put the hydrogen that's in the anti-coplanar orientation in a perfect orientation where the base is going to be so relaxed to pick up the hydrogen, to form the double bond and kick off the leaving group at the same time. So somebody might say, okay, well, but this is the less stable chair conformation. Yes, it is the less stable chair conformation. However, that's the more favored orientation in which you have the hydrogen and the leaving group in the axial position, anti-coplanar orientation. And that will be the one that's going to go through elimination, not the one where the halide is in the equatorial position. So that's very important to keep in mind, that this has to be applied only when you have a cycloalkyl halide. What if you have a straight chain? You're going to always look for the anti-coplanar orientation that's in the opposite side of the leaving group. And as I mentioned, the dash versus the wedge, or the wedge versus the dash, if you have a straight chain alkyl halide. Substitution or elimination. And I would like to use the flow chart to basically remind you of those possibilities. So this flow chart was looked at when we discussed SN1 versus SN2. Now let's look at the flow chart and now discuss all those four scenarios: SN1, SN2, E1, E2. So when it comes to a primary alkyl halide, it doesn't have more than two options. It's going to be either E2 or SN2. Now, the E2, in order for the primary alkyl halide to have an E2, to give you an alkene, you have to use a bulky base: terbutoxide, diisopropylamine, triethylamine, or the 2,6-dimethylpyridine. These are the examples of bases. When I see them with a primary alkyl halide, then the alkene will be the product. Other than that, substitution will happen. So SN2 is the only pathway for a primary alkyl halide. What happens if I have a tertiary alkyl halide? I have the possibility of running SN1, not an SN2, E1, or E2. So let's start with the easiest one, E1. When will the tertiary alkyl halide go through E1 mechanism? Only when there is a very weak base being used, such as water or alcohol, and there is heat involved. As you can see here, a weak nucleophile or base at elevated temperature. That's the only way how we could eliminate a tertiary alkyl halide. Other than that, will be a secondary, it will be an E2 pathway. And the E2 pathway, in order for it to happen, instead of the SN1, I will have to use a strong base. So if I have an OH minus or an RO minus, even if it's a methoxide, I will right away do an elimination type 2 to give you an alkene. That's the case of the tertiary alkyl halide. And this is very important to keep in mind. Other than that, it will be an SN1. Why would it go SN1 non-elimination? Then obviously you are using a strong nucleophile, but it's not a strong base, like an I minus, for example, or an S minus, or any of those examples of, or cyanide. All of these are strong nucleophiles, but they are not strong bases. So you cannot have an elimination product. What happens if I have a secondary alkyl halide? You cannot do E1. We already know that, just like the primary alkyl halide, but it can go through SN1 or SN2 or E2. And this is very important to keep in mind, that the secondary alkyl halide, in order for it to go through nucleophilic substitution type 2, it has to have a strong nucleophile reacting with, or a moderate nucleophile with polar A product solvents. In order for it to go through SN1, it has to use basically a weak nucleophile or a moderate nucleophile in presence of a polar product solvent. When will it go through E2? And this is very, very important note. Secondary alkyl halide will go through E2 pathway if a strong base being used, such as ethoxide or bulkier. How come I didn't say methoxide? Because if you use methoxide with a secondary alkyl halide, it will give you both products, SN1 and E2 product. If I am interested in the alkene structure, the E2 pathway, then I'm going to have to use heat to push the reaction go through E2. And this is important. Methoxide, the smallest base possible to be used, if it's used in the presence of a secondary alkyl halide, heat will push it E2, no heat will push it SN2. That's very clear. So make sure that you keep this in mind. Zaitsev's rule and Huffman's rule, we already mentioned that in the E1 and E2. So in the E1, Zaitsev product will always be the possible product. Now keep that in mind. I have to have a small base to be used to give me the Zaitsev product. Now the Huffman's product will always be favored when I use a bulky base, and the bulky bases listed in the flow chart are the ones that you are responsible for. The terbutoxide, the diazopropylamine, the trimethylamine, the triethylamine, and the 2,6-dimethylpyridine. These are the examples that you have to be responsible for. You also have the examples of or the choices of polar product solvents versus polar A product solvents. Make sure that you're aware of their structures in case you see them in exams or quizzes. So the PowerPoint slide, it basically shows now examples in which we see application of the flowchart. And my advice to you is to use the flowchart when you do examples from the homework and examples within the chapter. It's very important that you become familiar with what's within the flowchart. The flowchart cannot be used within an exam or a quiz. So keep that in mind, that do not rely on it to be available. You're gonna have to basically keep using it in your practice until you become familiar with it. And that's very important. So I have a primary halide reacting with a methoxide. I know right away it's gonna be an SN2 reaction because this is not one of the bulky bases. If I have a secondary halide with a methoxide, I have no heat. No heat, that means I'm gonna be forming both SN2 and E2. In fact, SN2 will be the major product. What if I'm interested in the E2 product? Then heat is needed with the secondary alkyl halide. Tertiary alkyl halide in presence of an alkoxide, regardless what alkoxide I use, it will always be the E2 pathway for a tertiary alkyl halide. More examples. So I have a tertiary alkyl halide, alcohol, that's a weak base, and heat. What is this sort of condition indicate? If I have a tertiary alkyl halide, alcohol, which is a weak base, weak nucleophile, and heat, this is the condition to give me an E1 pathway. So you will always form a carbocation, and that carbocation will end up basically giving you the major alkene to be the Zaitsev alkene. So the Zaitsev product will not be the minor product, which is the Huffman. So Zaitsev versus Huffman, Zaitsev will be the major product. And you also have the minor outcome going through in this approach, that will be the SN1 product. So if I'm having this question in an exam or a quiz, my final product, that's the major product, will always be the more substituted cyclohexene structure. So I got more examples. So I have a methoxide and I have a secondary alkyl halide. The fact that there is no heat, I will end up basically making two possible pathway, E2 and SN2. So the SN2, you're going to have the OCH3 in place of the BR. In the case of the elimination, this will pick up a hydrogen from the internal carbon versus the terminal carbon. The internal carbon will be the Zaitsev product. The terminal carbon will give me the Huffman product. So obviously the major product will be the Zaitsev product. So if this question appears on an exam or a quiz, you're going to be responsible to write both. I prefer that you write the SN2 product, the fact that there is no heat, as it will be the major product. So we could see here clearly the difference between E1 and SN1 and that's why the very similar approach in both mechanisms, we've seen there the similarity, and that's why in the secondary alkyl halide, if I use a methoxide, there will be a competitive pathway to give me basically the SN1 or the E2, or the E1, sorry, the E1. So that's the alkyl halide giving me an alkene, going through E1 versus E2. What if I want to have an alcohol to be the source of the alkene? Well, we need to remember that OH is a very bad leaving group. Why is it a bad leaving group? Because OH minus, which is the anion, it's a very strong base. There are two factors that need to be considered when I want to have a good leaving group. It has to be a weak base, and it has to be polarizable. So when those two factors are available, that leaving group becomes a good leaving group. So hydroxide, ethers, amines, F minus, all of these are weak leaving group, very bad leaving groups. So in order for me to go through elimination to end up having an alkene, this OH has to be activated. What's that supposed to mean? It has to be protonated to make a good leaving group. So that's why the dehydration of alcohols has to happen in the presence of an acid, and the reaction is slow to the point that I need heat to push it forward. So this reaction, it's reversible. It goes from the alcohol to the alkene in presence of an acid and heat, and goes back from the alkene to the alcohol to give you basically the alcohol through another mechanism that we're going to learn actually later on in chapter 8. So this mechanism, it's an E1 mechanism. It will never be an E2 mechanism, and we will see why that is. And because of the E1 mechanism, the rearrangement is always possible. And not just that, the reaction gonna always give me the Zaitsev product. So if I have the possibility of more than one hydrogen to be picked up through the mechanism to give me two different alkenes, I will pick the one that's gonna be the Zaitsev product. So this is the case every single time I have dehydration of alcohols. That's different from alkyl halides. So make sure that you apply the Zaitsev rule every single time you start with an alcohol to get an alkene. So let's look at the mechanism. What's the mechanism? The mechanism basically goes through steps. One, protonation of the alcohol. So the oxygen will pick up the hydrogen from the acid, and it has to be a strong acid. And once that's done, it's going to give me the protonated alcohol. So this is basically the a good leaving group now. Water is a weak base. So it's not an OH. Now we have water. So water is a good leaving group. Once it goes through the second step, it's going to basically eliminate that water, kicking it off to give you a carbocation. And this will be the rate determining step. So the protonation will be a fast step. The rate determining step in the dehydration of alcohol will always be the formation of the carbocation. Once you protonate the OH, it will be kicked off, giving you the carbocation. And here why you're always going to have to go through E1 when you have an alcohol to give me an alkene. And here's the reason why tertiary alcohol will be faster than a secondary alcohol, will be faster than a primary alcohol. The reason why, the tertiary alcohol will give me a tertiary carbocation. The secondary alcohol will give me a secondary carbocation. The primary alcohol will give me a primary carbocation. We already learned from previous chapter that stability of carbocations will always go from tertiary to secondary to primary, from most stable to least stable. Why that is? Two factors, hyperconjugation and inductive effect. And once you form that carbocation, now it's ready to go through the last step. That's the deprotonation. So the water will be, which was kicked off from the second step, will be the one that's going to pick up the hydrogen from the adjacent carbon, similar to the alkyl halide. You're always going to pick up the hydrogen from the adjacent carbon. And once you pick that up, that bond will be the one that's going to contribute to the double bond. So you end up having the alkene structure. So it's very common that you run acid catalyzed dehydration of alcohols. When it's a tertiary alcohol, you might not need heat. But if you go to a primary alcohol to be eliminated, you may actually need heat to push the reaction forward. So that's important to keep in mind. That tells you how reactive tertiary alcohol versus secondary versus primary. So this is basically an example where we've seen a tertiary alcohol going to be protonated to give you water. That's a good leaving group. So the protonated alcohol now is going to go through the slow step and that will be to kick off the H2O, and that to give you the tertiary carbocation. Tertiary carbocation is going to be reacting with water now. Water will attract the hydrogen to basically form a double bond to give you the Zaitsev product at the end. In this case, it doesn't matter which hydrogen to pick because all of them are the same. But in the case you have an example where you have a more than one hydrogen to be picked up by the water in that last step of the abstraction of the hydrogen, then always pick the hydrogen that's going to lead to the Zaitsev product, as it is the major outcome every single time you run dehydration of alcohol in presence of an acid. And we will be looking at examples to practice more on the concepts of E1 and E2 in the following part.